Right, so in today's lesson we're going to be looking at nucleophilic substitution of halogenoalkanes. Just a simple version, right? This is for AS chemistry. In A2 you expand your knowledge and look at SN1 versus SN2. So, nucleophilic substitution of halogenoalkanes. Let's take this one for instance, a simple halogenoalkane, that's chloromethane, and we're going to add to it sodium hydroxide. Now, I am just going to write in the hydroxide because the sodium is a spectator ion and does not partake in the reaction. Now, very important, I need to draw a dipole on the carbon-chlorine bond. Chlorine is more electronegative, so that becomes delta positive, delta negative. And that position there is attractive to those two electrons. Okay? This is our nucleophile. Nucleophile means it's attracted to positives, and the carbon has a positive charge density. So the electrons are going to move from the nucleophile and attack the carbon. The arrow, you can do it here, you can do it around the other side. Sometimes they do it that way. Of course, two electrons go in and two electrons have to come out. And they're going to come out from here. That bond there between the carbon and chlorine is going to be broken. Note, in both cases I'm using double-headed arrows. And in one step we can draw the product. Display it if you like. That's methanol. And the chloride ion, which left with the negative charge. Of course, if we use sodium hydroxide, our byproduct will be sodium chloride. And our main product here is going to be an alcohol. Do also note that the opposite reaction, that would be methanol plus, say, sodium chloride to make the halogenoalkane, that is not going to work. Okay, we've seen that one before, we used PCl5 for this one. That's not going to work because the hydroxide is a much stronger base than the chloride. So the chloride is the better leaving group in this case, whereas the hydroxide is going to behave as the nucleophile. Now there are more options here. Okay, we don't just have to use hydroxides as the nucleophile. We can also use cyanide, for instance, as the nucleophile. So let me just draw this one again. We've got the halogenoalkane, and now we're going to add a cyanide ion. Right? Note that that is triple bonded, carbon and nitrogen, and the lone pair is on the carbon. Well, same again. We've got the delta positive there, delta negative there. The lone pair attacks the carbon. Those two electrons are removed and go to the chlorine. And we end up with this compound. Carbon, triple bonded to nitrogen, and the chloride leaving group. Again, if we use potassium cyanide, we end up with potassium chloride. And this compound here, that would be ethane nitrile. Okay, ethane because there's now two carbons, and that group there is called a nitrile. It's one of the few ways that we have, especially in AS chemistry, to extend the carbon chain length. So we've gone from one carbon over here to two carbons over here. Okay, so now let's look at how ammonia behaves in this situation. I'm going to draw the same halogenoalkane, but this time I'm going to add ammonia, which is a weaker base, but it also behaves as a nucleophile. So let's not forget to draw the dipole here, the pair of electrons attacking that carbon, and those electrons coming out, double-headed arrows. And once you can do one, you can do them all. And that will now make this. And we've still got three hydrogens there, plus the leaving group chloride. Now, just to remind ourselves, we've got no charge there and no charge there, so that's no charge in total. We've got a negative there, we must have a positive somewhere. Where? Well, those electrons there were donated to that carbon, so that nitrogen now becomes positively charged. But these hydrogens, one of these hydrogens technically is datively bonded now to the nitrogen. So all we have to do is take that lone pair, return it to the nitrogen like that, and we're going to end up with this substance here with two hydrogens, three bonds on the nitrogen, and hydrogen given off, So the hydrogen and the chloride ion would make hydrogen chloride. Although we are in ammonium medium, so the ammonia, any additional ammonia in there with the hydrogen chloride would make ammonium chloride. But the main product being made here is this one called methylamine. And what curious thing about the methylamine is that the nitrogen here recovered its lone pair of electrons. Now, if we were to happen to have excess chloromethane, then there's no reason why the methylamine could act as a nucleophile in its own right and attack another chloromethane. So, I'm going to rub this out and we're going to start again. Okay, so I need a little bit of space here, so I'm going to use skeletal formula now. It's just a lot quicker and easier to draw and saves a bit of time. So let's go for chloroethane and ammonia. Okay, well when these two react, we're going to have a lone pair there, dipole on here, attacking that position, out comes the chlorine, and our end product will be our ethylamine in this case, plus hydrogen chloride. Okay, and that said, we recovered the lone pair of the nitrogen. So if we have excess chloroethane and we have methylamine being generated, there's no reason that the methylamine can't behave as a nucleophile in its own right. So let's draw that there. There, arrow. So you can do it from above or below, it's not too important. There we go, so out comes the two electrons from there. And what we end up is with this now. So we formed a bond from the nitrogen to that carbon there. So 1, 2, N plus the two carbons we've just added on, 1, 2, and nitrogen has 3 bonds. The third one goes to the hydrogen. Also the byproduct, hydrogen chloride. And we've recovered the lone pair on that nitrogen. Okay, so the diethylamine also has a lone pair on the nitrogen and can also act as a nucleophile in its own right. So let's add some more chloromethane, and now we're going to add this one here, lone pair. Get the dipole. Okay, you can do above or below, it's not important. Okay, so that can come here. I'll do it different every time just to make it look different. There we go. And we're going to end up this time now with, well, we've got this and we just bonded the nitrogen to that carbon there. So we have 1, 2, nitrogen, 1, 2, 1, 2 for instance, plus hydrogen chloride. Does it end there? Well, we've just recovered the pair of electrons on the nitrogen, so it can actually go one step further. So the triethylamine could react with excess chloroethane. Let's draw this. We'll do it step at a time because it gets a little bit complicated. There we go. Dipole. Lone pair attacks that carbon there. Electrons move on to the chlorine. In this case, we don't have a byproduct. In this case, we're going to make something that looks like. Okay, now we've got a nitrogen with 4 bonds. That gives it a positive charge. And our counter ion, the anion, would be the chloride ion. So that is a salt, which would be tetraethyl ammonium chloride. And lastly, to finish off, let's get rid of all this. Lastly, there's a special case scenario in which an elimination reaction takes place instead. So let's draw, for instance, this halogenoalkane. Chloroethane, and if the reaction with the hydroxide ion takes place in ethanol, right, the hydroxide ion in this case behaves like a base, and what it will do is it will attack a hydrogen on the carbon adjacent to the carbon the halogen is on. So in this case we would have this one here attacking that hydrogen there, that forms water. Those 2 electrons go here and the chloride leaves the molecule. So what we're left with is carbon, double bonding to carbon, with 2 hydrogens here, 2 hydrogens here, that's ethene. We form an alkene in the elimination reaction, plus the water, plus potassium chloride, KCl. Okay, that's an elimination reaction. It works much better when it's done in ethanol and also at high temperatures. There was an exam question once, which I'd like to just point out, which was, they did this one here. They said, okay, we have 2-chlorobutane and we add potassium hydroxide. Could have been sodium hydroxide, okay, don't forget potassium or sodium, they're just spectator ions. But it is carried out in ethanol at a higher temperature. Okay, well, that is a typical case for an elimination reaction. But it said, besides water and potassium chloride, which are the 2 main products? The 2 main products, well, if we have this hydrogen being removed there, then we're going to make this one with a double bond across the these 2 carbons here. But if we happen to remove this hydrogen instead, then we're also going to make the structural isomer there, but1-ene. Plus, obviously, the water as a byproduct, plus KCl. So we actually have 2 products in this case. I mean, you could also argue, well, we've got the trans but2-ene. Could we also make the cis but2-ene? And the answer would be yes. So technically, there's actually 3 different products. Be wary of that. It's AS chemistry, so they will try to ask you questions about geometric isomers wherever they can.